Okay, so let's start. So if you remember, right, in the last session, we completed decision trees, right, with examples and all. And we moved to ensemble method where we could create multiple decision trees, right? That was the discussion that we did, right? But I'll just go through once again this decision trees, right? Not in detail, but I'll just skim through so that you get an idea, right? Okay, till now, if you have any questions, do let me know first. If you are stuck somewhere, you have read through, you have some questions, you please let me know in that case. Vasu, any questions? No questions, okay. People are leaving. That said, another, I think, I don't know what is the issue, but people should not leave. Divija, do you have any questions?
No, sir, I don't have any questions.
Okay, right. So decision trees models are typically used for classification, right? We have looked into that, right? That, okay, at every node, we test a particular attribute, and depending on the number of values it can take, we have those many branches. If you look at this particular decision tree, right, or maybe this decision tree with respect to the data set that is given, right? So we are testing some attribute at every node, right? And depending on the number of values it can take, there are those many branches. This is the data set given to us. So if you look at, there are 4 input features and 1 output feature, which is play tennis, right? So our job is to predict this, whether I will go to play tennis, depending on the first input features as such. So first attribute is outlook. Outlook has 3 kinds of values, right? Temperature has 3 kinds of values, humidity has this much, windy has this much values, and we are testing one attribute at a time, right? And then according to the number of values, we are expanding the branches. The objective here is to move towards pure classes, pure partitions. If you look at outlook as overcast, right? I'm not expanding the tree further for this. This is my leaf node, because if the outlook is overcast, yes, I am definitely going to play tennis as per the data set. So for all overcast values, you will see the play tennis value is yes. So at this point, when it is sunny and rainy, I still have some impurity. Some records belong to yes, some records belong to no. So I have to expand it further, right? So we did techniques on expanding this also, right? Like randomly, I should build the tree, right? I picked up outlook here first. Why not temperature? Why not humidity? Why not wind? Right? Why only outlook first? So there is a formal method, right, that we follow, and that is known as entropy measure. Entropy measure is something, right, which actually mathematically gives me the value how impure the data set is. When I say impurity, right, impurity means, I mean, how many different classes, or what is the how many number of instances belongs to class A, how many number of instances belong to class B. I mean, if there's an equal split, it means its impurity is quite high, right? If you look at this, right, this is a form of a visual. If you see the left one, it has 2 kinds of records. One is green circles, another is plus. On the right side, you can see all the circles, green circles, right? So right side is more pure than the left circle. The reason being that is all records belong to the same class. So our objective is to move towards uh, minimum impurity, right? So we'll look at this impurity. So if you look at this, right, there are a good number of plus and green circles. If you look at this, plus are reduced, right? Only two, rest are green. So these are all instances belonging to one class. So this has a high impurity, this has a lesser impurity, and this has a minimum impurity, right? So when we achieve this minimum impurity level, right, that is where we stop further splitting the tree, but that particular branch. Entropy is one of the measure that we studied, right, last time, if you remember, that we can expand this formula pi log of pi, right? Summation pi log of pi. That's what we did, something like this. Sorry, let me put it. Summation will be outside. Yeah, this is the formula. Okay. So when there is an equal split, entropy will be high. So entropy value ranges from 0 to 1. When there's a records with 50-50 split, entropy will be high. When we have all the records belonging to one class, entropy will become 0, right? So information gain is one measure using which we can figure it out which particular attribute to choose at the root level, right? I mean, if I go to this particular example, right? So whether I should go with outlook, temperature, humidity, or windy, which one should I pick up at the root, right? So there is a formal measure to do that, and that is known as a kind of ID3 algorithm, right? Which makes use of entropy. So initially we calculate the entropy of the data set first. We know 9 records belong to yes class, 5 records belong to no class. So 9 by 14 is the probability that a record belongs to yes class. 5 by 14 is the probability that record belongs to no class. So I have to just plug in the numbers here. This is the binary classifier, so only we have two classes. 9 by 14 log of 9 by 14, 5 by 14 log of 5 by 14. Right? So you look at this, when you compute this, this is the overall entropy value that you are getting. This is the overall entropy value, and this shows how much randomness is there within the data. It is not one is the highest value, and that will come when we have a kind of 7 records in one class and 7 records in the other class. But it is little lesser than 1, so but still 0.94, it's quite high entropy, right? The second time I will check if I pick up outlook, how much entropy gets reduced. If I pick up temperature, how much entropy gets reduced? If I pick up humidity, how much entropy gets reduced? If I pick up windy, how much entropy gets reduced? Which which one will give me the maximum reduced? That is the attribute that I'm going to choose. Right. So if you look at this particular, yeah. So 2 by 5 log of 2 by 5, right? And 3 by 5 log of 3 by 5, log of 3 by 5 to the base 2. So if you look at this, outlook as sunny. So three records, sorry, belong to yes, no, and two belongs to yes. So when two belongs to yes, right? So total 5. So if I plug in those numbers, 2 by 5 log of 2 by 5, 3 by 5 log of 3 by 5, ultimately I'm getting this 0.971. And when it is overcast has all the records belonging to yes class. So this is a kind of a pure partition that I'm achieving. So probability of a record belonging to yes class is 1, while probability of a record belonging to no class is 0 when the value is overcast. So this term boils down to 0. For outlook as raining, so minus 3 by 5 log of 3 by 5 minus 2 by 5 log of 2 by 5. Again, the number comes as 0.971. Number comes as 0.971. Now, can you tell me how should I calculate the overall entropy? Can somebody quickly tell me how to calculate the overall entropy? This is with respect to 3 values. Now, how to calculate the overall entropy? If I choose Outlook, Outlook has got 3 values. With respect to different values, I have calculated the individual entropy levels. How to calculate the overall entropy? That is the question. Anybody who would like to speak, give some thoughts to it? We have covered it already. So now I have to go with weighted average kind of a thing, right? If you look at this, there are 5 records belonging to Sunny, right? So this value I am getting for Sunny. So I'll take 5 by 14 multiplied with 0.971 plus 4 by 14 multiplied with 0 plus 5 by 14 multiplied with 0.97, because this value is also 0.971 and there are 5 records for Rainy also, right? So this is what I will do. And if you look at this, this is largely what is done here. And ultimately, you are getting the entropy value as 0.693. So it was something 0.940 at dataset. When I choose Outlook, it reduces to 0.693. So we calculate the information gain, like 0.940 minus 0.693. This is the information gain, which is 0.247. Similarly, what I will do, I will calculate this information gain value for the other attributes. Now let's look at, if I pick up temperature. Temperature can be hot, mild, and cool. Hot has got 4 records, cool has got 4 records, this has got 6 records, right? And within hot, if you see, this is no, no, and yes, yes. So 50% records belong to no, 50% belongs to yes. Directly, without calculating even, I can simply say this has a higher entropy of 1, 50-50 split, right? If I look at this, 3 by 4 records belong to one class, 1 by 4 records belong to other class. So you look at this, this is 0.811 when it is cool. But when it is mild, 1, 2, 3, 4, yes. And if you look at no, 2, right? So you'll expand that 4 by 6 log of 4 by 6, 2 by 6 log of 2 by 6. This is what you are getting. Again, you will calculate weighted. Now, how the weights will change? 4 by 14 into this value, 6 by 14 into this value, plus 4 by 14 into this value. Sum this across, and what is the value you are getting? Just see. You are getting 0.911. So 0.940 was the entropy of the data set. Now you are getting 0.911. If you subtract it, the information gain is 0.029, very minimal. Now, if I have to compare both, right? If I have to compare both, and look at this, 0.247 and 0.029. Which one do you see is better? Which one? If I look at the outlook and this temperature, right? Which one is giving me better results? If I have to choose one of these two, okay. Now this lecture thoroughly we have covered, and I guess that was covered even 2 weeks back, if I'm not wrong. Since the topics are related, so I'm covering it once again. But are you guys even looking at the content, what is being covered? Tell me frankly. Are you guys taking notes? May I have some response, please? Okay, how many of you are actively doing this particular course, and how many of you submitted the assignment? How many of you have submitted the assignment? May I get some response, please? Hello? See, when you go blank, right, in every session, now I cannot say you are a mature guys now. You are working professionals. You should know that okay, what I have to retain in my mind, right? And when you are coming blank, it is very, very disappointing for a faculty member. Should I keep on speaking then? Cover it up. Nothing you will ask. Why should I cover the problems then in the class? If you cannot pay attention to those problems, why should I pay? I mean, why should I put my efforts, right? Because solving a problem in a class takes a lot amount of effort. And when it is covered right, I expect also from your end that okay, you will do it diligently. And I want you to remember few things because the other concept is related. Every time I cannot repeat the things entirely. How many of you know about decision trees? See, without knowing the concepts, why are you coming to? I mean, I don't know, like how you are managing the course and all. If the idea is just to pass it, I don't know what. Even if you are going to pass it, you should have something in your mind, right? Can I have some communication? Can somebody please speak out where the challenge is? Then from your batch, I've seen you put up, okay, this faculty is not that good, this is not. Are you guys putting effort equally? Everything is not a cakewalk. You also have to raise your level in order to understand the niche technology. Now let me call names then, otherwise this is something which is very, very annoying. People will have to speak. Jatin, Jatin, are you there? Okay, why we are here? You joined a class, right? You joined this class. You want to listen to something. I'm asking something. If you don't communicate, then why we are here on a Saturday? Think twice, right? What you are doing. At least do justice to what you are doing. Jatin is not there. Lakshmi, Lakshmi, Naveen, are you there? Nami, Pragati, Prashant, Shreya. Shreya, are you there? At least somebody can speak out, right? Hello? If you don't know decision trees, and if I cover in ensemble, then what is the fun, right? Now it is your problem. You will have to do it. Now ensemble problems also, like I'm not going to cover it in too much of detail. I'll give you the concept. It's up to you how you want to manage it. I am tired right now, right? To ask you many things. Okay, we can drive the course the way you want, where the challenge is, but you will have to give effort. Without effort, you cannot understand. It is not like that, okay, you spent 2 hours here, right? Might have been okay by now if you would have put some significant effort. Okay, let me continue then. I will continue speaking, then there's no point in discussion, right? Vasu, what is the challenge? I'm coming again to you.
Yes, sir.
This decision tree class, right? I think 2 sessions ago we covered it in detail. Now, where are the challenges?
So I am aware of the decision trees.
Okay. So when I'm
Like,
asking a question, then
yes, sir. So last class I was there, but last to last class I was not there. I have to
uh,
revisit that session
no,
recording.
but why you have not revisited till now? The question is that.
That I will do, so that is on my part.
See, it's your when you are missing out on something, if you persist on it that you want to do something right in this particular domain, then you will have to find out time for this. Nobody in life is going to come to help you out. Nobody is there to listen to this, that, and all, right? We appreciate that you are working professionals, but at the same time, we expect something that, okay, this is very bare minimum that I am expecting. And being working professionals, you have some accountability, right, at your job. Similarly, you have joined this program. So at least take something out of it. Time and again, I'm saying, don't simply add degrees to your resume. Take something out of it. What you can implement it at your workplace. Soon you will see one assignment on it. And let me tell you what Professor Omshri has told me, uh, that out of 61, some 32 people have submitted the assignment. You see, almost 50%. 50% are not even submitting assignments. Do you really want to pass this course or not? I'm not sure. And she extended the timeline also. I'm not sure now how many of you have submitted within the extended timeline, but that is the stats, what it says, right? 30 out of 60, right? And we have to also take one Viva. Soon I'm going to start with Vivas also. See, we are doing a lot of calculations, right? With temperature, with this, but information gain I am calculating. The gain will be highest, which is reducing more entropy, more randomness. Reduction in more randomness means high information gain. So 0.247 value is greater than 0.029. So 0.247 information gain is greater than 0.029, meaning that picking up outlook will be better than picking up temperature. Similarly, we can do it for humidity as well. And when I did all the same calculations with humidity, it came out to 0.5151 as information gain. So again, with outlook, it was 0.247. So still outlook is better, right? Out of all three. And now finally, it's windy. Now windy is giving me the information gain of 0.048, right? Still outlook is better. If you look at this is the information gain from outlook, temperature, humidity, windy. So outlook clearly wins here to be at the root node, and the similar process can be followed for the other nodes to complete the tree. I asked you to do this at least and solve it and come up with this complete tree, all the calculations. Nobody has shared that. No one of you have shared this. If somebody will solve it, right, the way it is solved in the slides, right, you will get the concept thoroughly, the maths behind it. Start from here. It will take some time.
Yes.
Yes, who's this? Yeah, please speak out whatever you want to speak. Was it you or somebody else?
No, sir, I was not.
Okay. People are not even, see, you are a working professional, but people are not even speaking, right? That's the biggest disadvantage to me, right? When I don't get to know. So you pick up this as root node as the outlook, right? And then this example was covered, right? Where we were trying to find out an error with respect to the rule that we have written. I can explain you the same example, but with a different thing. Overcast, right? Uh, yes, no. 4 records belong to yes, no, 0 records belong. Sunny, yes, no, 2, 3. Raining, yes, no, 3, 2. Right? I have a rule now. Sunny means if the outlook is sunny, I will not play tennis. Let's say that is the rule. I am coming up with a rule. Sunny, I will not play tennis. For Sunny, how many records are there? 1, 2, 3, 4, 5. Out of those 5, 2 are yes, 3 are no. So 3 records comply with this, but 2 records do not comply with the rule. So there is an error of 2 records. So we put 2 by 5 as the error. Overcast, yes, right? So when there is overcast, I am going to play. All 4 records belong to this. No records belong to no clause. There is no error. So 0 by 4 error. And when it comes to raining, right? Raining, yes. If it is raining, I'm going to play tennis. So this is my rule. Raining, yes. But if you look at this, out of 5 records, 2 of them say no also. So the error is 2 by 5. So total error, if I look at it, it's 4 by 14. Similarly, I can, yeah.
So for Sunny and no, there are 3 records.
Sunny and no, there are 3 records. Yes.
Then
Yes.
how come we are calculating error as 2 by 5?
I am saying there is a rule that,
Okay,
okay,
that is a predefined rule. We are not
yeah,
okay. Okay, so then I got it. Negative
I'm,
scenario is yes.
yeah, whichever is not complying with the rule, right? That is an error. I'm saying if it is a climate is sunny or the outlook is sunny, I'm not going to play tennis. There are 5 records, 3 comply with that, 2 do not. So error is 2 by 5, right? Not 3 by 5.
Yes.
Does that make sense? For rainy, the rule is different. If it is rainy, I'm saying yes. I'm not saying no. If the rule is rainy, no. What is the error that I'll get? Let's assume there's another rule. If it is raining, I'll not go to play tennis. What is the error for this rule?
So 3/5.
3/5. If you focus, nothing is very tough. It's very simple. Similarly for temperature, hot, mild, cold, right? So I have some rules. This is all calculations done, right? Some hot, no, right? Hot, no. 2 records belong to yes, no. 2 belongs to yes. So error is 2/4. If I look at temperature, mild, yes. Mild, yes, I'll go. So error is again 2/6, right here. Cold, 3/1. So error will be 1/3. Sorry, 1/4. This record is error. So total 5/14. And if you look at this humidity, again I'm getting 4/14. And if you look at this windy, again I'm getting 5/14. And now these are the errors that I'm getting. Now minimum error we can pick, but you can see there is a tie. There is a tie between humidity and outlook. What should I do now? So in that case, we'll have to choose the one in which there is a pure partition. I mean, if you are seeing some zero error in any of these two, pick up that. So you look at this portion, this is giving you a better split, kind of a leaf node that you are getting. You need not to further expand it, right? I mean, you need not to write further rules and all. So I will prefer this first rather than humidity. That's what it is, right? So outlook is chosen first, and then further things we try, right? So this is how we do it, right? Another example that's there. And now you can do this example yourself. Whether the loan, now these are the 4 attributes which are input features. This is output. Whether the loan is approved or not, right? And this is the error with respect to this. Young no is one rule defined, right? Middle yes is another rule defined. Old yes is another rule defined. So what is the error? 5/14, right? So you look at this, we have checked the error for job, house, credit, right? And this is what you are getting. And again, we have a tie here, right? So we are picking up house as this, right? Because it is with lesser number of branches, and again, there is a pure partition among it, right? So a lot of examples are there. You will have to do it yourself, right? All this has been covered, and even this portion also has been covered. That okay, there's something called an overfitting, right? By this time, all of you should know what an overfitting is, because there have been questions in the exams, overfitting, underfitting, and all. And decision tree might also get overfitted, right? If you come up with a very complex tree which is very deep in means, if you know the height of the tree in data structures and algorithm course, height is more, right? It means the tree is more deep, and you are trying to satisfy each and every uh, record, right? Whatever we have taken examples, 14 records, 15 records, these are very small data sets, and we are able to achieve a perfect tree. But when we have 1 million record, 10 million records, I may not. So if I try to fit out each and every record and classify it purely right into pure partitions, then my tree might get overfitted. And once overfitting is done, then how there should be ways to kind of reduce it, right? So first thing is you can avoid the overfitting. So you limit the basically you can say the tree depth, right? And at a time, right, you also, while splitting the tree, you also sort of do some statistics, right? Whether this is going to improve the results or not, only then I should go for splitting, otherwise not. Significant results, right? If you have already gone through probability and statistical course, and you assume some hypothesis, and then you do some statistical tests. After that, you say whether this null hypothesis is accepted or rejected at 5% level of significance or 10% level of significance, something like that. Same thing when you are splitting, right? A very deep tree further. You try to figure it out whether this further splitting will be of significant advantage or not, right? And then you further split it, otherwise not. Second is the pruning thing that you can use. You can kind of remove the subtrees, right? Which you feel that, okay, they are not making much sense, or well, you have grown the tree to a full length and then you are pruning it. You are reducing the tree, right? Basically, you are trying to merge some of the nodes, right? Trying to reduce the depth of the tree. So both the things are possible. I've covered it in detail in the last session thoroughly. Occam's razor is one principle. What it says is simpler trees are better than the complex trees, right? So if you have got this kind of a tree, right? I'm further splitting it unnecessarily, right? So does this further splitting is helping me to a significant level or not? Or maybe I can simply stop at this point. Because it is saying, okay, at this point, right, I may not be able to achieve pure partitions, right? But making it overly complex also does not make much sense. As long as I have achieved my reasonable performance metrics and my tree is simpler, it is more generalized one, I will try to stick to that, right? At this stage, let's say I can give you an example. If there are some 10,000 records falling here, and out of those 10,000 records, I'm saying some 995 records belong to one class, 5 records belong to other class. So anybody coming to this path, this is class X, this is class Y, right? For X, there are 995 records. For Y, there are 5 records. It is not a pure partition, right? But if you look at this, most of the records belong to class X. So anybody coming on this path, and I'm stopping here, I will classify that as X class, right? I'm not going to split it further because of 5 records, because it is going to make my tree overly complex. Maybe within one more attribute test, I may not even get those 5 records correctly classified, right? So there's no point in expanding the tree further if I'm not getting a significant advantage. So Occam-Fraser says that the decision trees which are small and represent the correctly classifying the data, that is the better one, right? Otherwise, you will end up into kind of a NP hard problem if you try to classify each and every. Right? Look at this. This is the decision tree that we have built, right? Earlier. So now you see outlook sunny, temperature hot, humidity normal, wind strong, right? And play tennis snow. So outlook is sunny. I'm coming to this part, right? After that, humidity is normal, right? So then it should say yes, right? But this is what is expected out of the tree. What they're trying to say is, if I am now, what I'm saying is, this was a perfectly classified tree. this another record is added to the data set. Earlier there were 14 records, now we have added 15th. So now this tree is not sufficient, right? Because play tennis is no, already given, right? Play tennis is no. But if I go by this tree, what I'm getting is humidity is normal, right? So I will classify it as yes. Now what further I will do here is one record since falling here, I will further start splitting the tree. So this new example causes the splitting of second leaf node. This is first leaf node, this is second leaf. So this will further split. And now when I further splitting this because of the newly record added, right? This is a small tree. Maybe if I'll be able to fit within one more test. But what if it is a very large tree, right? Simply addition of one record. I should not further split it, right? Otherwise, it will land up in overfitting. Keep it more generalized one. Right. So these are the strategies in general, right? Avoid overfitting. Don't stop growing the tree earlier before it comes up with the perfect classification. Second is allow the tree to overfit and then you prune it. Prune it means you try to reduce the nodes. So these are the things we have covered it in detail, right? Look at this, right? What is pruning? This is the tree given to me, right? This is the original tree. But if you look at this particular portion, right, is pruned. And if you look at this particular portion is also pruned. So I have at age only, right, agitate, whatever the attribute test we are doing, right? This particular thing, we are not testing it, right? Because most of my records are soft, right? Classified as soft. So these are the leaf nodes, soft, none, hard, right? So I am simply saying it is soft. If you look at this, right? Most of my classes are records belong to none. Splitting this based on this spectacle prescription, right? Is not helping me much. So I'm just pruning this, right, and keeping this as none. Soft or none, that's all. And it becomes a kind of a simpler tree than this, and this is called as a pruned tree. It depends on the number of records falling, right? If on age, let's say soft is having some as I mentioned earlier example, these many records, and this is only having 5, right? So I can just merge them out, right? That's it. Similarly, if I look at this, right, this might have almost, let's say, 990 record. This is having some 10 records and all. So, of course, most of them fall into this none category. So I will simply replace this with none and close this tree, right? So this is what we are trying to avoid, overfitting. So this was all about it, right? And you can go through it. I have almost spent 40 minutes on it, 40 to 45 minutes once again. And now session 10, we have started it in the last session, but I'm again going to work out on it, right? So I'm going to cover conceptual parts today. So this first few slides are again from the previous chapter only, right? Overfitting and all that which we're dealing with. Now, what is ensemble learning? So we have talked about various classification models, right? If you talk about, we started with Naive Bayes. I'm writing NB. We did logistic regression also. then SVM, support vector machine, then decision trees, right? These are the 4 classifiers we have studied. Now, what is ensemble, right? If I have to ask, okay, let me put it in a different way. If I use any of these classification model on a particular data set, right? Which one will give me the better results? Any thoughts? I am going to use a classifier, right? These are the 4 different classifiers we have studied: naive-Bayes, logistic regression, support vector machine, and decision trees. What do you think? Which one will work? Which one will give better results? Can I say that, okay, naive-Bayes will give always better results? Do you remember naive-Bayes classifier? The question was given in the exam also. Logistic regression question was given in the exam also. SVM also, one single pointer question was given for that. Decision trees I have just covered right now. So there is no single classifier that you can say, okay, this will always be best, or this will always be best, or this will always be best, or this will always be best. Depends on what kind of data that you are dealing with. Basis that, and once you have applied all these model to various data sets, you will get an experience and see, okay, this kind of data we can use this algorithm, and this kind of data we can use this algorithm. But can we have a better technique than this? Then there comes another technique known as ensemble learning, which is ensemble of classifiers, right? Ensemble of classifiers. I'm not going to use one classifier, right? I'm going to use multiple classifiers, right? And idea is to come up with a classifier that combines the individual decisions. So ensemble of classifiers, why and why ensembles work? There is a technique which is used, right? Ensemble, that is bagging. Another one is boosting, right? So both the techniques I will just quickly go through. Now different classifiers are there, and I am going to combine the results of each classifier so that I can get a better results. That's whole idea of ensemble learning is. So look at this. Successful ensembles require diversity. Idea we know, right? There are multiple classifiers, and our idea is to construct a classifier that combines the individual results. But when this will produce good results? When these ensembles have a diversity. If they do not have a diversity, then of course we cannot say that, okay, this ensemble method, or when we are trying to combine multiple classifiers, it is going to work. Diversity means everyone is making some different kinds of mistakes. Classifiers should make different mistakes and can have different types of Bayes learners. Right? I'm not going to use the same algorithm. So Bayes learner for one could be naive-Bayes, another could be SVM, third could be logistic regression. It could be anything, right? So we can use it for regression, we can use it for classification. Regression, right? I am not sure if you remember or not. We predict a continuous attribute where there is some numeric value I am predicting. predicting a house price, predicting a stock price, right? That is regression. So when I have put multiple models for regression, this is giving me, let's say, some house price prediction as 15 lakhs. This is giving me some 16 lakhs. This is giving me 14.5 lakhs. This is giving me some, let's say, 14.7 lakhs. So what I can do is, with this kind of thing, I can go and take the average of it. That is when I'm doing regression. But when I'm doing classification, right, it is giving me one category. Let's say the class is yes or no. This is giving me yes. This is giving me no. This is the next classifier is giving me yes, then no, then yes, then yes, then I'm having this, right? What I can do is, now there's no average that I can take, of course, right? But I can definitely take the vote, right? Vote of each classifier. So then I will can go with the majority voting. If number of votes for yes are more, I will take the final classification as yes. The number of votes for no are more, I will take the final classification as no. So I'm combining multiple classifiers, right? Now this is what a simple diagram which explains ensemble technique, right? So we are going to improve the classification accuracy, but how? By aggregating the predictions of multiple classifiers. So how do we do that basically? I have my original data set, right? It might have 1 lakh records. And there are, let's say, 10 classifiers I want to make. So I will divide them into some sort of, let's say, 10 data sets, right? Each having 10K record. I'll train my each classifier with those 10K records. And I have now classifiers here ready. Build multiple classifiers. C1, C2 up to C10 will be the classifiers. And then I'm going to aggregate the predictions of each of those classifiers, right? So this is the whole idea. You have some data, right? You are dividing it into multiple parts. Each part you are giving it to one classifier. Classifier will make predictions, will be trained and will make predictions. Then the output of each and every classifier you are aggregating. That is the whole idea, right? So this combined output of the classifier is expected to be better than that of individual classifiers. That's the whole idea. So instead of using one classifier, use multiple classifiers. There is a statistical proof also, right? Assume that you have some 25 binary classifier, each has an error rate of 0.35, right? And that is some error rate. And if all of them are identical, right, then what will happen? They will vote the same way on each test instance, and the ensemble error rate will also be kind of 0.35. So if you have identical classifiers, right, which do not have a diversity, you are not going to get a reduced error rate with ensemble. Diversity has to be there, right? Assume we have 25 binary classifier. Each has an error rate of this. If all 25 classifiers are independent and errors are uncorrelated, ensemble method may only make wrong prediction if more than half of the base classifiers predict incorrectly. More than half. Look at this, right? So this is what this statistical formula says is, you have 25 base classifier, right? Each has an error rate of 0.35. Each has an error rate of 0.35. So with that epsilon value, it is going to make an error with 1 minus epsilon LU, it is going to make predictions, right? It is going to make predictions for that correctly. So you look at this, e raised to power I plus 1 minus e raised to power 25 minus I, and even if the error rate of individual classifier is 35%, because they are independent, they are uncorrelated, they have a diversity, they are making different kinds of mistakes. Ensemble is making 6% error out of 35%. That's a statistical thing that they say. If they are not they do not have a diversity, they are making the same mistakes and all, ensemble will also make the same level. But if they are independent, they are diverse, they are making different kinds of mistakes, then if more than half of the base classifiers predict incorrectly, then the ensemble will predict incorrectly, more than half, because majority voting will go to more than half, right? And that's the problem. Then the ensemble will give the wrong results. And you see the power of ensemble now. 35% error in individuals, but if they are diverse, 6% error in ensemble. Look at this comparison of 25 base classifier when the error rate is varied. This is base classifier error, right? And this is ensemble classifier error. So this dashed line when the base classifiers are identical. So ensemble is also kind of going to make the same error, right? Whatever the base classifier is making an error, ensemble is also making the same error. If it is making 0.2, it is also making 0.2. If it is making 0.4, it is also making 0.4. But when you have different things, right? Then you have a solid curve like this. When the base classifiers are independent, right? I mean, they're trained with different models and all, right? So different error rates are there. So this is what it is, right? After that, maybe initially the base classifier is giving an error rate of 0.2, it is at error 0, right? If base classifier is giving an error of somewhere around, let's say 0.4, it is giving 0.15 around, right? This is the point. If I take it up, let me take this, right? This point, it is 0.4 something, right? But it is little above than 0.3. So even the ensemble classifier error is less. When you look at this, right, this is the point where I think the error is mostly the same. We have 0.5 here and 0.5 here, right? Exactly. And then after that, if you look at this, this is 0.7, but this is lesser, right? This is 0.6, and this is ensemble classifier error is more. And if you look at this, this is lesser, right? And this has reached 1, right? Almost. And at this point also, this has also reached 1, right? So depending on what kind of base classifier error is, right? Ensemble classifier error also varies, right? If it is identical, you see the blue line, both ensemble as well as base classifier error doing the same mistakes. The moment the base classifier error goes beyond 0.5, right? That means 50% of the time it is making a mistake. Ensemble classifier error further increases. So ensemble classifier perform better than the base classifier when the error is smaller than 0.5. So necessary condition for ensemble classifier to perform better than a single classifier is base classifier should be independent of each other, should do better than a classifier that performs a random guessing. So random guessing means if it will be kind of 50-50% kind of a thing. But if it is going to make a better guess, let's say 0.7, 0.3, 0.7, 70% of the time it is accurate, 30% of the time it is not accurate. Then Bayes classifiers is doing better, right? It's not randomly guessing. And then you build a ensemble on top of them, you are going to get a better result from ensemble. Otherwise not. If the Bayes classifier accuracy is less than 0.5, you are not going to get a good result. Ensemble methods work best with unstable Bayes classifiers. Classifiers that are sensitive to minor perturbations in the training dataset due to high model complexity. Right. Unpruned decision trees, artificial neural networks, right? They make the model very complex and all, and if you change the data set a bit, maybe this will not work. And okay. Low bias in finding optimal decision boundary, high variance for minor changes in the training data set, or that is where the ensembles will work, right? Now, example, movie rating, right? Maximum voting. The result of maximum voting would be the final result, right? Rating by 5 friends. One is 5, 4, 5, 4, 4, right? So, of course, 4 is the max voting, so we can go. Other is we can take average 4.4, weighted average, right, at some places, because I am giving some classifier a more weightage than the other classifier. That could also be possible depending on what kind of problem I am solving, and I am giving him the more weightage. 0.23, 0.23, 0.18, 0.1. So if you see, this classifier is having, these two classifiers are having more weight than these three classifiers, right? So I will multiply it with each of them and then take the weighted average, and then that could be one way. Depending on the kind of problem that I'm going to solve, basis that I'm going to choose max voting, averaging, or weighted average. So what are the methods for constructing an ensemble classifier? Now we have one training data set, right? As I told you, okay, you divide it into multiple parts, train classifiers, and then take the output of that classifier and then build the ensemble one. But let us look at some formal methods. How do I construct an ensemble classifier? The first one says is by manipulating the training data set. Second one, by manipulating the input features, by manipulating the class labels, by manipulating the learning algorithm. These are the 4 things that you see, right? And let's look at each one of them. When I say by manipulating the training data set, I've got one training data set, right? Now, when I'm going to choose from, I told you, right? 1 million records. You divide it into 10 parts, maybe 1 lakh records in each, and then you build classifiers with 1 lakh records, and then you combine the results of those 10 classifiers. Now, how do I randomly choose a sample for a particular classifier? That is now what we are going to look at. Multiple training sets created by resampling the original data. I have some data, right? I'm not going to divide it as such. I'm going to do some sampling, right? I can sample the data as per the equal probability. When I say equal probability means I have some classes, right, for prediction, maybe class A, B, C. So my each data set should have data points with equal probability belonging to class A, B, C. Second one, I can go with the weighted one, right? Third is determines how likely it is that an example will be selected for training, right? So basically, the idea is if you look at a broader level, I have been given some data set. Right, this is my data set. I might have to sample it for one classifier, then another sampling I can do for another classifier, right? And then third sampling and fourth and so on. Now, how do I sample it, right? How do I manipulate the training data? There are two techniques from bagging and boosting. And that is what makes the ensembles more powerful, these two techniques, right? And once you will look at this, how they are making it more powerful, you will have a better understanding, like why ensemble is giving us better results and under what cases it will work. So we will come to bagging and boosting soon, but let us look at by manipulating the input features. Manipulating the input features, right? You might have many features. I don't want to use each and every feature for each and every classifier, right? I might have 100 features. For classifier C1, I might sample some features out of it. I'm not going to give 100 features. Subset of input features is chosen at random from overall collection of features. So each training set has different feature set. Ensemble method that manipulates the input features as one of them is random forest. You must have heard this random forest algorithm, right? So you are taking some attributes, not all the attributes or not all the features, and then building a classifier. And then another classifier, then another classifier, right? And this works well with a dataset that contains highly redundant features. Some duplicate features here and there are there, right? So instead of horizontal partitioning, right, it is more of a vertical partitioning. Because data set, when I partition horizontally, I am partitioning it record wise. When I am partitioning it horizontally, features, maybe 10 features I am giving it to classifier 1, another 11 to 20 features I am giving to classifier 2, maybe 21 to 30. I'm just giving you a hypothetical example, right? This way. Third is by manipulating the class label. This is typically used when you have very large number of classes. So far, we've talked about binary classes, right? Yes, no, 0, 1, and so on. I might have very large number of classes. And when I do have those many classes, what I typically do is transform them into many binary class problems. I'm not going to keep it as a multi-class classification, rather a binary class. Randomly partition the class labels into two disjoint sets. Class 0, class 1. Train a base classifier based on this class reassignment. Repeat multiple times, one for each base classifier. So I am going to choose some subsets, right, which has two classes, and I am going to train base classifiers basis that. So each base classifier, right, what will predict? A test instance with respect to its binary class subset. So some two classes are given to one classifier, some another two classes are given to another classifier, and so on. So each base classifier is going to predict a test instance with respect to its binary class subset, and all classes in the subset receive a vote. Class with the highest vote wins. Right. We will see in the bagging technique also in more detail by manipulating the learning algorithm, so that applying the algorithm on the same training data may result different models. That we are doing it keeping it diversity, right? Naive Bayes. Then I am using, let's say, decision trees. I'm using SVM, right? Instead of choosing best splitting attribute at each node, randomly choose one of the top k attributes for splitting. If I want to build multiple decision trees, right? So I am manipulating the algorithm here. Now, there's a concept of weak learners, right? If I go back to this diagram, classifier 1, classifier 2, classifier 3, classifier 4, and so on. Each of them is known as a weak learner because they are not trained on the complete data set, right? So each of them is a weak learner. Right? So that's one thing. How to combine the weak learners, right? There are three popular combination method. Bagging considers the heterogeneous weak learners, focuses on reducing the variance. Boosting considers the homogeneous weak learners, focus on reducing the bias. Stacking considers heterogeneous weak learners, right? So we will look into this, right? Let us see what bagging is. Bagging, also known as bootstrap aggregating, which aims to produce an ensemble model with low variance than its individual components. So low variance means the test error is going to reduce, right? So what happens? It first learns several homogeneous weak learners with high variance independently, and then combines them using an averaging process. So then what is the important thing here is, I am being given a data set. How do I train the multiple weak learners? Maybe I have very limited data set, right? Then how do I do training for each of the weak learners? Should I feed the same data to every weak learner? And if that is the case, maybe I'm not coming up with the diversity then, right? So the idea is to use this technique known as bootstrapping. So the first step of bagging is, right, bootstrap aggregation. So first is bootstrapping. What do we typically do in bootstrapping, right? It's a resampling technique in which the samples are drawn with replacement from the original data set. You remember your things, right? You said when you were doing permutation combination, a ball is drawn randomly from a bag. What is the probability and so, right? When a ball is drawn from a bag, it is kept back, right? And when you next time resample, right? So it could be the same ball that is coming out. So when you put a ball back into the bag, that is with replacement, right? And when you do not, that is without. So it is used to generate the multiple bootstrap datasets from the original datasets, right? That's the same thing. We have this given dataset is this, right? There are 5 records, 1, 2, 3, 4, 5. So there are some input feature. This is my output, right? This is my output. Now, when this is the output, how do I train multiple models? How do I come up with multiple? My original data set is limited. And if I say, okay, I want to train 5 classifiers, can I give 1 record or maybe 10 record up? I'm just giving you an example. With 1 record, obviously you cannot train even a classifier, right? It will not be up to the mark. Even with 5 points also not, but just a smaller data set example, right? So that how we generate more data sets from this original data set. Look at this. Again, 5 records. This is the initial data set. These are the 4 variables that are used, right? And this is what the predicted variable, whether that person has this particular disease or not, right? So one point is this is just for an example sake that we have taken. In real world problems, the initial data size should be large enough to capture most of the complexity of the underlying true distribution. These are only 5 records, right? So, but to understand what bootstrapping is, look at this now. 5 points are there. Randomly, I'm going to select some points, right? Some records. So you see, the first sample that we randomly select is this, right? Second, you can see second is this, third is this. But what is important is the same record is appearing twice, right? So this is what a bootstrap data set is. It's with replacement. Second ball, the ball can be drawn again from the sample. So this is a bootstrap data set that we have created. 5 records were there, but if you look at this, right, this is repeated and this is repeated. So this is what a bootstrap data set is, that you might have some records with repetition. So this process is repeated until we create a bootstrap data set for every weak learner. So how many weak learners we want to train, right? I will come up with those many bootstrap data sets. Maybe here the record 1 and 3 were repetitive. In other, maybe record 2 and 4 may be repetitive, and so on. Okay. So let's assume we have 3 weak learners, and therefore we create 3 bootstrap data set that's shown in the diagram. Maybe you are not able to read it, but assume it. This is something taken from here with some repetition. Now what bagging does? It is going to train a data set, right? Train a model. We call it as a weak learner, right? Another model, weak learner 2. Another model, weak learner 3. The best part is now we have independent data sets, right? So I can train them in parallel, right? This is being trained, this is being trained, this is being trained. So 3 data sets, 3 weak learners we have trained, right? So bootstrapping is sampling the data set for a weak learner with replacement, right? And now what is bagging that we are doing is we are going to it's bootstrap aggregation. That's what bagging is, right? So we will aggregate the results of the weak learners. So this is f1x, right? This is f2x, this is f3x. I am doing the average of what every model is giving me. I'm going to do the average of that. So we aggregate the weak learners into some kind of averaging process. Right? May not be every time average, but here it is shown as average. Okay, f1x, f2x, and f3x, and we are taking the average of that. Look at this. There are several possible ways to aggregate multiple models for a regression problem. It's very clearly mentioned, regression problem, because you are going to get a numeric value. The output of models can literally be averaged to obtain the output of the ensemble model. And this is what simply the average formula is, right? First model has given 14, second model has given 16, then 15, then 13. You have take an average and see, okay, this is my final output. So what is bagging? Bootstrap aggregating, right? Bootstrap aggregating technique uses these subsets to get a fair idea of the distribution. The size of subset is created by bagging, maybe less than the original, right? At that time we said, okay, 5 data sets we created for it, but it may be less than also the original data set. It's a sampling technique in which we create the subset of observation from the original data set with replacement, right? When you sample with replacement, items are independent. One item does not affect the outcome of the others. You have 1/7 chance of choosing the first item and 1/7 chance of choosing the second item if you have 7 items, right? So this is the overall summary of bagging, right? If 2 items are dependent or linked to each other, right? When you choose the first item, you have 1/7 probability of picking an item, assuming that you don't replace the item. Next time you have 6 items to pick from. So this gives you 1/6 chance from second and so on. So if you put with replacement, you will get a different kind of data set. If you put without replacement, you are going to get different kind of data set, right? So multiple subsets are created from the original data, selecting the observations with replacement. A base model, weak model, is created for each of these subsets. These models run in parallel, are independent of each other, and the final predictions are determined by combining them. That's what we have been studying, right? Original data set, subsets, done. Then train one model known as weak learner from each of these subsets. Each learner will give you an output, then combine the output from different learners. That's the whole idea about this bagging technique. Sampling with replacement, build a classifier. Each sample has a probability of 1 minus 1 by n selected as the test data. Training data, 1 minus 1 minus 1 by n raised to power n of the original data. Right. Find a collection of 10 simple thresholding classifiers that collectively can classify correctly. Each simple or a weak classifier is, right, it's a class +1 or -1 depending on the values, yields the lowest error, which k is determined by the entropy minimization, right? So you are trying to come up with a threshold. Basically, if the x value is less than k, right, you say, okay, class is +1 or -1, right, depending on which value yields the lowest error, right? And this k is determined by the entropy minimization. So some threshold is we are going to pick up, right? Basis which I am going to classify the record. Now let us understand this. Consider this one-dimensional data set is there, right? One-dimensional data set is one input feature, and this is my output feature. Right? If you look at this, 0.1, 0.2, 0.3, the value is 1, 1, and 1. 0.8, 0.9, 1, the value is 1. For these middle values, 0.4 to 0.7, it is -1. Right? It is -1. So classifier is a decision, right? Decision rule says if x is less than k versus x greater than k. X is less than equal to 0.3 and x is greater than, let's say, equal to 0.8. Split point k is chosen based on the entropy. We have already understood what entropy is. It's randomness. It's randomness, right? So I want to split the data set, right, in such a way that if it is less than equal to k, right, I am getting some value of y, right? If it is greater than that, or I mean, if x is not less than k, it's on false, so I am going to get this particular value. But we have something +1 for less than 0.3 and greater than 0.8. And in between from 0.3 to kind of 0.7, we have -1. Right? So how should I come up with this kind of thing that x is less than equal to so and so? Is this is going to be +1 and this is going to be -1. So that is what we will calculate entropy point. Look at this. Bagging round 1, right? When we pick up the first sample, it has picked up 0.1, 0.2, 0.2 twice, right? 0.3, and then 0.4 twice, 0.5, 0.6, 0.9 twice. This is what the first round is, that sample that we have taken, right? So till this point, if you look at it, right, this is a kind of a pure thing I am getting, right? I know that. And here there is some sort of impurity I'm getting, but this is what the split I am going to do, 0.35, and this is greater than 0.35. At least one part I am correctly able to do, the other part there is some error in that. If you look at bagging round 2, right, these are the values that are picked up. 3 times you see 1, right, and here you see 0.4, 0.5. So this is another kind of a sample drawn, right? Now if I look at the entropy point, either I can put up entropy value here, right, or here, but since there are more records this side, right, so this will be a better suitable entropy and this will be the better entropy. So that's what we have chosen. The left part will have some errors, definitely. It is there are some errors, yes, there are, right? It's sort of -1, it should be, right? It should be +1, yeah. Third one, you see here 0.1, 0.2, 0.3, and then a lot of -1s, right? So of course the boundary is here because there are 3 records. I can put a boundary here, but there are 2 records, that will be that entropy value will not be good. But if I put it here, so if you look at this, right, this is the what the split is, and bagging 4 is giving me kind of this split, right? This bagging round 5 is giving me this split, right? So I am going to get different kinds of splits, right, as such with respect to the different bagging rounds. 1, 2, 3, 4, 5 rounds I have taken, right? You look at 6, 7, 8, 9, 10. Similarly, we have taken the other rounds. Randomly drawn samples, right? Put some. So now you see each classifier is learning something, right? Some threshold value each classifier is learning, below which either there is a +1 or -1, or above which, right, depending on what kind of things we are doing. If you look at bagging round 10, it has picked up all which are 1, right? So it is simply saying x less than 0.05, y is 1, greater than 0.05, y is 1. But with respect to regional data set, you can see there are -1s in between, right? So by training these different ones, right, we are getting this. Look at this. So bagging round 1, split is 0.35, left class 1, right class -1, 0.7 this, right? Okay, let me see, go back to round 2. Yeah, less than 0.7, right, and greater than 0.7. Split point this, right? Less than 0.7 is kind of a -1, right? So you look at this, for each classifier, we are able to come up with a left class and right class, what we have done here, right? This is all 1, right? So this is, you can say, all 1s. This is all, if I look at minus less than 0.75, it is -1, other one it is 1. less than 0.75, it is -1. So you see, these are different examples, but they are coming up with similar kind of results, right? This is also similar results coming up. So 0.35, 0.7, and 0.75 are some boundaries that we are getting, right? Now, this is what the summary of bagging example as such is, right? Now, if I look at the ensemble part, assume the test is same as the original data, right? Use majority vote to determine the class of ensemble classifier. Majority voting. Look at this. If I pick up x as 0.1, x value is 0.1, right? What first classifier will do? It will classify it as 1, right? Because 0.1 is less than 0.35. It will classify it as 1, right? That is what we have put 1. X is equal to 0.2. X is equal to 0.02, 0.2, right? It is going to classify it as again 1, the first classifier. Till 0.3 it is 1, rest it is -1, right? This is what it is, right? When it comes to round 2, 0.7, right? Okay, now when it comes to round 2, right? It has learned kind of, let's say, 0.7 as the boundary, but less than 0.7 it is taking 1, both ways it is taking 1, right? Because the reason I'll tell you, there are 4 records here which is 1, so this is quite straightforward. But there are 3 records belongs to 1, another 3 belongs to no. It's a kind of a random guess. It could be 1, it could be -1. So we are taking it as 1, right? So let us put it as both as 1. All ones are coming, right? Round 3, the value for the round 3 is 0.35, same as first, right? The result is also same as first. Then is 0.3, right? Left class is 1, right is -1. So till 0.3, it is 1, rest all is -1. The result is same. For fifth also it is same, right? Because the value is 0.35. Next, the value is changed to 0.75. Right? So till these, right, the values are -1, other one. So 7, 8, 9 are like this. If I look at 10th, the value is 0.05. So it is also classifying everything as 1. But when I look at this, now I have to take the maximum voting out of this, right? 1, 2, 3, 4, 5, right? 5 is saying 1, 4 are saying -1, right? And this is also saying 1, right? So basically, if you sum this, right, if the sum is positive 2, right, so sign is 1. If it is negative, sign is -1, right? That's what simple way to do that, right? Basically, you can calculate this particular classifier given as 1, 1, 1, 3, 4, 5 ones. 1, 2, 3, 4, 4 -1, and then 6 also 1. So 1, 2, 3, 4, 5, and 6. 6 ones and 4 -1s. So obviously 1 is this particular class wins, right? So in other ways, because classes are 1 and -1, they have taken a sum where the sum is positive, so it will be one class. Where the sum is negative, it will be a negative class. And if I look at this way and now compare it with my training data, right, it is 100% correct. Training accuracy has changed to 100%. Though the individual classifiers have an error, but when I put it in an ensemble, it is 100% correct. If you look at any of these, right, individual classifiers are not correct. Even if I took at 0.35, left class is at, what is the left class? 0.35. This is 1, right? But right class, it's not completely -1. There are 4 records -1, but 2, 1 also. Right? 2 or 1 also. So this is what it is, right? So accuracy of ensemble classifier is 100%. And this is the bagging algorithm, right? Simple steps. K is the number of bootstrap samples you want to do. So you take bootstrap samples, train a base classifier on each bootstrap sample, and then you pick up, right, argmax value, right? So basically, which one, how many classifiers vote for a class X, how many classifiers vote for class Y, maximum vote you take it and then classify it accordingly. This is what bagging is. What is boosting? So boosting, so bagging, what we did, we are bootstrapping the samples, right? Bootstrap samples, we are taking some K samples, and basis that we are training the classifier, and then we are taking maximum vote, right? That is what we are doing. When it comes to boosting, this is another technique. This is iterative procedure to adaptively change the distribution of training data by focusing on misclassified record. So it's not like that I'm going to divide my data and build all the classifiers at the same time. It is not like that. All n records are assigned equal weights for being selected for training, right? Unlike bagging, weights may change at the end of each boosting round. So second time when I'm going to resample, so records which have a more probability to get selected will have a higher weight than the records which have lesser. How does this things make sense, right? Let us understand that. Unlike bagging, where each instance had an equal chance of being selected, focus on the instances that are hard to classify. So initially, when we do first sampling, it is same as bagging, right? With that, we train a classifier, and we now understood that, okay, this data it is able to classify better, but specifically, let's say class B records, the classifier is not able to pick it up. So second time I will see, okay, how many class B records are there? I should give them a high weightage. My model is not trained enough to recognize class B records. So I want to give those. So which are difficult to classify in a first training instance, right? After first model is trained, that records got more weight in the future rounds. Look at this boosting. An iterative procedure to adaptively change the distribution of train by focusing on the previous misclassified record. Initially, all n records are assigned equal weights. Unlike bagging, right? Weights may change at the end of each boosting round. Records are wrongly classified will have their weights increased in the next round, and records that are classified correctly will have their weight decreased in the next round. This is your original data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Now, if you look at this, 7 is picked up, 3 is picked up, 2, right? 8, 7, 9, 4, 10, 6, 3. boosting round 2, right? 5 4 9 4 2 5 1 7 4 2. Boosting round 3, right? So whichever example you find, right, whichever class you find, it's hard to classify. Its weight gets increased and more likely to be chosen again in the subsequent methods. Now, in the subsequent rounds. Right? If you look at 4, it could be possible that 4 they were finding hard to classify, and that is why they have chosen 4, right, multiple times in the boosting round 3. They've chosen 4 multiple times in the boosting round 3. And if you look at this, right, here also, three times, right? So whichever class is hard to classify, that we are picking up. So kind of we are trying to train a model on those on which it is not able to predict it correctly. So AdaBoost is one of the techniques, right, which follows boosting. So there are base classifiers C1, C2 up to CT. Error rate of the base classifier is given as this, right? Sum weighted average, right? We are putting it. And this is the importance of a classifier. And if you look at this, the error, I said there, this portion, right? Importance of classifier, it is high when the error is low. The moment the error it is increasing, right? Error is increasing, importance is decreasing. If you see 0.6 error, see the importance has come almost to negative, right? And even if you go, if the error is 1, importance is further decreasing. So these are inversely proportional, importance and the error. If you increase the error, importance goes down, right? And that should be the way to rank the importance also. This is how you are going to update the weights, right? If any intermediate round produces error rate higher than 50%, then the weights are reverted back. And the resampling procedure is repeated, right? Because 50% error is something it is not able to predict. High impurity in the data set, right? That is kind of models we don't want. Let us look at this example of AdaBoost, right? The same example. So again, we want to classify, right? 1 and -1. So which value should we choose? So we're going to pick up some different samples every time. Look at this 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.8, 0.9. So this is what? Initially the weights are equal, right? 0.1 is the weight given to every thing and some total weight is 1, right? Round 1, right? The weights are equal and each has a probability, equal probability of choosing. So 0.1 is first chosen, 0.4, then 0.6, then 0.6, then 0.6, 0.7, 0.7, 0.7, 0.8, right? 1. So we have y as 1 here, 1 here, 1 here, right? So obviously this kind of boundary will be chosen. This kind of boundary will be chosen, right? But when you give this class, now let's say it is giving, let's say 0.75 as a boundary, right? So you say below 0.75 -1, above 0.75 1. Let us say this is the case. But when you give it 0.2, it will classify as a value of -1. 1 also it will classify as a value of -1. But actually for point 1, 2, and 3, it is 1, right? So point 1, 2, and 3, the values you see, the weights are increased. While for the others, it remained same because the values it was predicting was correct. So we are not going to change. Only thing is there are better chances of now taking these samples into consideration. Point 1, 2, 3, which were misclassified. And now you look at this further. Point 1 has better chance. Point 2 also came in multiple times, and point 3 also came multiple times. And now you see all ones, right? All ones are there. So regardless of anything, it is saying, okay, this is going to give me 1. So next time what will happen is for others, right? 0.4, 5, 6, and 7 specifically. This, the weights have increased, while which are correctly classified, right? Their weights have decreased. Because every time it is going to give 1. So 0.123, 0.891, they're all ones as per the original data set. So they 0.4567 is where is the problem. So this next time only these samples will come into picture. So 0.2 has come, 0.2 has come, then 0.4, 0.4, 0.4, 0.4, 0.5, then 0.6, 0.6, and 0.7 has come, right? And now you see it can generate a boundary like 0.3 is one boundary it can generate. So greater than this is 1 and less than this is, greater than this is -1, less than this is 1. So again, then 0.89 and 1 will create a problem, right? For that, the weight should increase. So what is happening is, this is what the first model learns, right? This is what the first model learned. This is round 1. And if you look at this, these were incorrectly classified, right? And for them, the weight would have been increased. If you look at 1 by 10 summation j, this 0.03, classifier importance is this much. Weight was 1. So 0.03 is the error, right? Right. 0.03 is the error it is producing, and importance is 1.738, right? Second time you are updating it like this, right? So this is what you are getting, 1.83, right? 0.568 into 3 plus 0.018 into 7, right? This is what we are doing, right? So basically, how it is updating this next time, if you remember, right, the weights came to 0.311, 0.311, 0.311. How this came? That is what they're trying to explain. So 0.03 was the error from the first, and this is the model importance 1.738. Update happens as this 0.1 into e raised to power 1.738. 1.738, 1.738, this model importance, right? 0.1 e raised to power minus 1.738 minus 1.73, because we want to decrease their importance and increase its importance. So positive 1.738, negative 1.7. So proportionately increase which are misclassified, proportionately decrease which are correctly classified. So this is 1.83. So if you normalize it sort of thing, right, it will be 1. So this is how AdaBoost works. Prediction made by each base classifier is weighted as alpha. Instead of using a majority voting scheme as bagging, AdaBoost combines the prediction of using weighted voting based on the importance of each classifier. Now look at this. Round one, this is the split point, right? Left class -1, right? So importance is this. Round two, split point is this, right? Importance is this. Round three, split point is this, and importance is this, right? So when we do this, right, based on importance. So round one, it is -1. So the importance of this is 1.738. -1 into 1.738, 1 into 2.784, 1 into 4.1194. So basically add these two, subtract this. So this is 5.16. So positive sum is there. So 1. Prediction is 1. Now for these two, right? Again, it is 5.16 value will come. So positive 1. So again, this is same thing. Now 2 -1s, right? 1, 1. So of course, 1 into this and -1 into this, these two terms are negative. So overall result is going to be negative, right? So depending on the importance plays an important role, right? Accordingly, it is going to classify. This is the AdaBoost algorithm, which you can read, right? Now, what random forest does? Let us quickly go through it because it's a conceptual thing. Ensemble method specifically designed for decision tree classifiers. Random forest, they are actually growing many trees. Ensemble of unpruned decision trees. Each base classifier classifies a new vector of attributes from the original data, right? As I told you, right? It is going to pick up some attributes. Final result is on classifying the new instance voting. Forest chooses the classification result having the most votes. So you're coming up with multiple decision trees. What is the formula, right? Introduce two sources of randomness. One is bagging and other is random input vectors. Each tree is grown using a bootstrap sample of training data. We know what bootstrap sample is, right? Random vector is at each node, the best split is chosen from the random sample of m attribute instead of all. So we are doing some feature selection for every tree also, right? Both the things are combined. Look at this original training data, randomize it. This is D1, D2, right up to. Use random vector to build multiple decision trees. We have created some random vectors, right? And then decision trees are built. I'm going to combine the result of all the decision trees, and this is what random forest is. So multiple trees it is growing, and that's the name is random forest. So draw a bootstrap sample of size n, grow a random forest tree to bootstrap data, right? By recursively repeating the following steps, select m variables at point. So that's the same thing that we will have to do, right? And to make a prediction to a new point x, we do regression average of the results, or for classification, majority voting is used. So both ways we can use this particular thing, right? So what are the characteristics? It can solve both classification regression problem, can handle large data set with higher dimensionality, because I am going to divide my dimensions into multiple parts, and each tree will get a different dimension. It can handle thousands of input variables, identify most significant variables, right? That is also possible. If from one decision tree the results is coming up very good, right? That means it has those features are good. Model outputs importance of variables, which can be very handy in future, right? What it may do is may overfit data sets that are noisy. When number of variables is large, the fraction of relevant variables is small, and the random forests are likely to perform poorly when m is small. Relevant variables are small, right? At each split, the chance can be as small as that relevant variables will be selected. 3 relevant and 100 not so relevant variables, the probability of any relevant variables being selected at any point of split is 0.025. 3 by 10. Random forest can feel like a black box approach for statistical models. You have very little control on what model does. You can at best try different parameters and random seeds. That's all we can do. Look at this. Comparing the accuracy of decision tree classifier against 3 ensemble methods: decision tree, bagging, boosting, random forest, right? This is decision tree. This is the output of bagging, better, boosting even better, random forest as good as boosting. So you look at this, right? These methods consistently gave you better performance than the decision trees, right? These are giving you consistently better performance. Look at this particular three Irish data set. Here, this performance is better, but still bagging is equivalent to that, right? But overall, these bagging, boosting, and random forests are giving you better results. That's all about bagging, boosting. One topic, stacking, we will talk about conceptually, right? So this ends this particular thing, and maybe I will sometimes also show you some Python codes on that, right? But whatever the EC1 components are given right to you, kindly take it seriously, submit it. Only then it will make sense that you are doing a course. I'm not sure how many of you have understood what exactly, because nobody speaks up, right? So even if you have a habit of speaking up, that will be good. But I think nobody has that. Few people only came out. Just wanted to know how many of you got an idea of ensemble methods. Did you learn something on ensemble methods? People who were right from the beginning? Many of you have joined in the halfway. Vasu Gupta. Yes, Vasu. Did you get some learning on ensemble? Shweta? See, until and unless you keep pen and paper handy with you, this will not work. And you need to have a Python notebooks with you, right? How this, and whenever you are doing bagging, boosting with Python datasets, you need to check it out, what kind of sample it has generated, right? Anyway, I will try to show it, but AdaBoost and boosting also, you should know what we are trying to improve. Okay, if nobody has anything to say, we can wind up. Shweta, you don't want to speak? Yamuna, Krishnan, any doubts from your end? Lakshmi?